Just look around and you will find that there are many physical quantities in our everyday lives like temperature, pressure, energy, mass, and time that do not point in any direction in the spatial sense. We call such quantities as scalars. A single value with a sign specifies a scalar. For example, temperature of -2 degrees Celsius, or say a mass of 5 kilograms, or pressure of 20 Newton per meter square. We deal with scalars by the rules of ordinary algebra, like addition of similar quantities and so on. A vector quantity is a quantity that has both magnitude as well as direction. Some physical quantities that are vector quantities are displacement, velocity, and acceleration. There is a very unique style of representing vectors. Graphically, we represent them with arrows, whose length indicates the value based on the scale of the graph, and the direction is given by the direction of the arrow. The simplest vector quantity is displacement or change of position. A vector that represents a displacement is called, reasonably, a displacement vector. If a particle changes its position by moving from A to B, we say that it undergoes a displacement from A to B, which we represent with an arrow from A to B. Remember that a vector can be shifted without changing its value if its length and direction are not changed. The arrows from A to B, from A1 to B1, and from A2 to B2 have the same magnitude and direction. Thus, they specify identical displacement vectors and represent the same change of position for the particle. The displacement vector tells us nothing about the actual path that the particle takes. Displacement vectors represent only the overall effect of the motion, not the motion itself. The only exception to this rule is a type of vector called the position vector. It is a general way of locating a particle and is a vector that extends from the origin of the coordinate system to the position of the particle. As a particle moves, its position vector changes in such a way that the vector always extends to the particle's position from the reference point, that is, the origin. If the position vector changes, say from R1 to R2 during a certain time interval, then the particle's displacement during that time interval is delta R, which is equal to R2 minus R1. Let's try to understand this operation. Here, the displacement delta R is equal to the difference between two vectors, R1 and R2. The negative of a vector is the vector having the same value but opposite in direction. The sum or difference of vectors is mathematically defined, and there's a specific way of doing it. Let's take a look at it. Suppose we want to add two two-dimensional vectors A and B. Let's do a little exercise to understand how to add these two vectors. On paper, sketch vector A to some convenient scale and at the proper angle. Now sketch vector B to the same scale with its tail at the head of vector A, again at the proper angle. The vector sum is the vector that extends from the tail of A to the head of B. Vector addition, defined in this way, has two important properties. First, the order of addition does not matter. Adding A to B gives the same result as adding B to A. Second, when there are more than two vectors, we can group them in any order as we add them. The vector minus B is a vector with the same magnitude as B, but the opposite direction. Adding two vectors B and minus B would yield 0. Thus, adding minus B has the effect of subtracting B. We use this property to define the difference between two vectors. That is, we find the difference vector D here by adding minus B vector to the vector B. Note that the rules for addition and subtraction hold for vectors of all kinds, whether they represent velocities, accelerations, or any other vector quantity. However, we can add only vectors of the same kind. For example, we can add two displacements or two velocities, but adding a displacement and a velocity makes no sense. Adding vectors geometrically can be tedious. A neater and easier technique involves algebra, but that requires that the vectors be looked at in reference to their rectangular coordinate system. A component of a vector is the projection of the vector on an axis. To find the projection of a vector along an axis, we draw perpendicular lines from the two ends of the vector to the axis, as shown here. If we know the angle the vector makes with the axis, we can use trigonometric ratios to find these projections. Like if the vector makes an angle theta with the x-axis, the projection of the vector A along x-axis would be A cos theta. The same vector would make an angle 90 minus theta degrees with the y-axis. So the projection of the vector along the y-axis would be A cos 90 degree minus theta, which works out to A sin theta. If we square and add both these equations, we'll get the following: ax square plus ay square equal to a square multiplied by sin square theta plus cos square theta, and that would be equal to a square because sin square theta plus cos square theta is 1. And taking square root of both sides, we'll get a equal to square root of ax square plus ay square. And if we divide the two equations, we'll get ay by ax equal to tan theta. The projection of a vector on the x-axis is its x component, and similarly, the projection on the y-axis is the y component. And the projection along z-axis is its z component, which is 0 in cases where our vector is totally in the xy plane. The process of finding the components of a vector is called resolving the vector. A unit vector is a vector that has a magnitude of exactly 1 and points in a particular direction. It lacks both dimension and unit. Its sole purpose is to point, that is, to specify a direction. The unit vectors in the positive directions of the x, y, and z axis are labeled as I hat, j hat, and k hat respectively, where the hat is used instead of an overhead arrow as for other vectors. Unit vectors make it very convenient to represent vectors in terms of their components. For example, a vector A with components ax, ay, and az can be written as A equal to ax I hat plus ay j hat plus az k hat. We saw earlier how we can add vectors geometrically. Another way to add vectors is to combine their components axis by axis. To start, consider the statement r equal to a plus b, which says that the vector r is the same as the vector a plus b. Thus, each component of r must be the same as the corresponding component of a plus b. That is, rx equal to ax plus bx, ry equal to ay plus by, rz equal to az plus bz. Two vectors must be equal if their corresponding components are equal. So, to add two vectors a and b, we add their components axis by axis to get the corresponding components of the sum r. And then we combine the components of r to get r itself. This is how we do it. The vector r would be equal to rx I hat plus ry j hat plus rz k hat. And the magnitude of r can be calculated as r equal to square root of rx square plus ry square plus rz square. And the angles this vector makes with the various axes can be derived by playing around with rx, ry, and rz along with the trigonometric ratios. I'd suggest you give it a shot and let me know if you get stuck. There's a reason we use the letter r here. That's because we call the sum of two or more vectors as a resultant, and that's where r comes from. Another very important operation on vectors is multiplication, which we use very frequently while working with vectors. There are three ways in which vectors can be multiplied, but none is exactly like the usual algebraic multiplication. Multiplying a vector by a scalar and multiplying a vector by a vector, for which there are two ways. One way produces a scalar, which is called a scalar product, and the other produces a new vector, which is called the vector product. If we multiply a vector A by a scalar S, we get a new vector. Its magnitude is the product of the magnitude of A and the absolute value of S. Its direction is the direction of A if S is positive, but the opposite direction if S is negative. To divide A by S, we multiply by 1 by S. The scalar product of the vectors A and B is written as A dot B and is defined as A dot B equal to AB cos phi, where A without the arrow on top of it is the magnitude of the vector A. Similarly, B without the arrow on top is the magnitude of the vector B, and phi is the angle between A and B, or more properly, between the directions of A and B. There are actually two such angles, phi and 360 degree minus phi. Each of them can be used because their cosines are the same. As you can see, the right-hand side of the dot product equation here has only scalars. The dot product, therefore, is a scalar quantity. A dot product can also be regarded as the product of two quantities, the magnitude of one of the vectors and the scalar component of the second vector along the direction of the first vector. If the angle phi between two vectors is 0 degree, the component of one vector along the other is maximum, and so also is the dot product of the vectors. If instead it is 90 degree, the component of one vector along the other is 0, and so is the dot product. Therefore, it is easy to see that the dot product of the unit vectors with themselves is 1 and with each other is 0. Also, please note the following. A dot B would be equal to B dot A. We can calculate the dot product of the two vectors by writing them in terms of their components. From what we just saw about the dot product of unit vectors, if we use those to open up the brackets here using distributive property of multiplication in the right hand side of this equation, we will get A dot B equal to AX BX plus AY BY plus AZ BZ. The vector product of A and B, written as A cross B, produces a third vector C whose magnitude is AB sin phi, where phi is the smaller of the two angles between A and B. You must use smaller of the two angles between the vectors because sin phi and sin 360 degree minus phi differ in algebraic sign. The direction of C is perpendicular to the plane that contains A and B. We determine the direction of C by using what is known as the right-hand rule. Place the vectors A and B tail to tail without altering their orientations, and imagine a line that is perpendicular to the plane where they meet. Pretend to place your right hand around that line in such a way that your fingers would sweep A into B, through the smaller angle between them. Your outstretched thumb points in the direction of C. If you sweep B into A instead, you'll be calculating B cross A, and your thumb will point in the opposite direction as compared to what it did when you swept A into B for A cross B. And therefore, B cross A is equal to minus A cross B. By applying the right-hand rule, we can calculate the cross product for unit vectors, which works out as follows. I hat cross j hat is equal to k hat, j hat cross k hat is equal to I hat, and k hat cross I hat is equal to j hat. Also, the cross product of any unit vector with itself is 0. Using these and the unit vector notation, we can find the cross product of A and B by writing them in terms of their components. This session, like all the previous ones, mainly focused on building your conceptual understanding. What you do need to do is to also solve a lot of problems. We will solve some good problems in the next session, but till then, keep practicing and do let me know if you get stuck somewhere. Have a great time doing physics. Bye-bye.